so we can move a little quicker. So if I'm going too fast, say in low, slow down, or I have no idea what you're talking about anymore, you've got to review, okay? So, and I'm videoing for Zonky because he's not here. You guys have your reading guide? Yeah? So I'm going to say, take a minute and talk to your buddy who's sitting next to you on the answer, and you're going to share out. So you guys are going to talk about kinetic and potential energy. Diamond and Chelsea, thermal versus heat. And then you guys talk about chemical energy. Okay? You guys are going to talk about what state function is. You guys are going to talk about E, Q, W. Heat versus temperature. And then heat capacity versus specific heat capacity. And what equations have you seen so far? Okay? Take a minute. And I have the question number indicated. Pretty much.
State function is a value that depends only on the state of the system and not on the system. That state. And for the example, thermal energy, temperature, and pressure.
Now as potential. Makes sense?
All right, are you good? Thumbs up if you're ready-ish. Okay, first participation grade. Here we go. Where's my stuff? Here we go. Kinetic versus potential energy. Go. This is number 4 on your reading guide. So if you want to look at it and make sure you're visually looking at it as well as hearing it. Go for it. Kinetic and potential.
Kinetic energy is energy of motion.
Okay.
Potential energy is energy an object has because of its position.
Or because of its chemical makeup. So for us, we're mainly looking at chemical composition, because that's, we're in chemistry, right? Yeah, we're looking at chemical composition. But we also can look at the position of subatomic particles to other subatomic particles. So for example, if two oppositely charged ions or subatomic particles are closely together, their position might lead to them having higher potential energy than being far apart. So that can be a part of chemistry, but it's on the nanoscale level. Next, thermal versus heat.
Thermal is the energy associated with the temperature of an object, and heat is the flow from the temperature.
Okay, so is heat a thing? Is it tangible? Not really. It's a movement of energy, right? But thermal energy, we're saying it's related to the temperature. Well, temperature is directly related to, or actually, well, yeah, temperature is directly related to one of yours. Kinetic energy, right? So these things are all really intertwined, but their definitions are different, and the way you use the terminology is different. So when we say heat, we're talking about heat flow. When we say thermal energy, we're talking about inherent energy that's based on the temperature that those particles are residing at, and that temperature is really related to how fast they're moving, which is actually kinetic energy again. So those are all very intertwined. And in chemical energy?
Chemical energy is energy stored in the bonds of chemical compounds.
Okay, so it's related to the bonds, and it's related to the particles and their position. So it's really, chemical energy and potential energy are very, very similar for us, because they're all related to the composition or to the position of the particles. Okay, state function. What is a state function?
A state function is a value for the state of the system, and not how the system arrived at that state.
So not how it arrived at state. So what does that mean to you in real people terms? Or do
What
you
the
know?
value is at the time, not concerning any other time.
Okay, so if I ran from here home, and I went down 85, then 29, and then blah, blah, blah to Union Street, I could go that way, or I could go down Speedway, and then 29, and this way, or I could go like all the way through Ridge and back. Basically, what's my starting point? Here, what's my ending point? Home. Doesn't matter how I got there. My initial and my final are the same. So the state function is just basically related to where you start, where you end. The pathway is it's the independent of the pathway, how you get there. So it's a state function because sometimes it's really hard to measure the in between stuff. Like specifically for chemical reaction, it can happen in 1 step or it can happen in 15 steps. But that stuff in the middle, sometimes we don't care about. We actually care about where it starts and where it ends. So that's actually something we're going to start labeling change. And anytime you have change, like let's just say change in energy, what you do is you do energy final minus energy initial. And that's how you figure out the change of energy or change of state function. It's about initial and final and how they compare. Okay, 20. These 3 variables, what are they?
Delta E is a change in energy.
Okay, so internal energy is kinetic energy plus potential energy. Q?
Stands for heat transfer.
Okay, so that's heat.
And then W is work done. And then the equation is delta E equals.
You guys saw this, yes, in your book and your reading. This is an equation we're going to use a lot today, specifically on one of the problems that we'll hopefully start. Okay, so these are going to be all related, and for us, work is going to be something very different than work done in like physics. So it's related, but it's based off a motion or a movement of volume. All right, heat versus temperature. What is the difference?
Heat is the change of thermal energy.
And temperature is the average temperature.
Okay, so this is average kinetic energy, so that's based off of like a single piece of matter. And this is what? I'm sorry, I'm putting transfer. Transfer of energy. Okay, so this is between 2 objects. This is the inherent component of one object. So we just need to use those appropriately. Heat capacity and specific heat capacity.
Heat capacity is the quantity of heat required to change the temperature by 1 degree Celsius.
Okay, the quantity of heat, which is measured in what unit? Heat. Joules, okay? The quantity of heat required to change something by
1 degree Celsius.
Okay, 1 degree Celsius. I don't know if it was 1 on that side. 1 degree Celsius. Okay, I didn't hear anything about amounts of stuff. Okay, tell me what that's different from this.
Specific heat is like the ratio between the heat and the unit of mass to raise the temperature by 1 degree Celsius.
I keep getting that degree symbol on the side of the 1. Okay, that's kind of weird, but okay. So this one does not include mass. This one does include mass. Which of these is an intensive property? Intensive property means that it does not depend on the amount of mass.
Heat capacity.
Specific heat capacity actually does, because see how we're already dividing by mass? So it's already as a ratio per amount of mass, so it doesn't matter how much you have of it. If you have 1 gram of it or 100 grams of it, anytime you divide by the amount of mass that's there, you're already accounting for the mass, so therefore it's independent of the amount of mass. So this is an intensive property. So this one, you can probably imagine, the more I have, the more energy that's going to be related to it. Therefore, that does depend on the amount of mass. That isn't an extensive property. You probably read a little bit about that in your book. But now you can kind of say, we're just organizing it. Okay, equations. Shout them out. Okay. Q equals MCAT.
Delta E equals Q plus W.
Okay, so the internal energy equation. This is the internal heat equation. Okay, so when you say MCAT equals MCAT, what are you actually referring to? Right, so this might be system, and this might be surroundings. Anything else? Delta H of products minus delta H of reactants. Is that what you said? Okay. So these are different equations we're going to see. So this one and this one you guys have seen before in Honors Chem. This one and this one you've not seen. Maybe you have seen. Maybe I mentioned that one once. But we're going to deal a lot with it. So this unit is on chapter 6, which is thermochemistry, and then chapter 16, which is thermodynamics. But thermodynamics is just a little bit of an extension of thermochemistry. Okay? So let's do one more, and this one's me. You guys have seen these before. What is this called? Heat curve, right? It's not a curve, but it's called a heat curve, right? I don't know why we make up these lovely names. So this is called a heat curve. This is temperature. This is heat added. Now we know the difference between temperature and heat, so we actually know there's a significant reason why these axes are labeled as they are. As a substance, okay, so you can see the phases that I'm going through. What's this first phase? Solid. This is at low temperature. This is liquid, and this is gas. All right, so you can see your states of matter. What are happening at the plateaus? So what's that phase change?
Melting.
Melting. And that has a name. It's called delta H fusion. Buzz. Delta H of fusion. Does that ring a bell?
Yes.
Some of us, okay. So delta H of fusion. Fusion means to melt. So there's an enthalpy. Delta H is called enthalpy. Enthalpy of fusion is the energy that it takes to melt whatever mass of, like 1 mole of water in this case. This one's evaporation. So this one's called delta H vap, right? Delta H vaporization. So that one's actually related to the amount of heat it takes to vaporize 1 mole of liquid to 1 mole of that same gas. So in this case, what actually is happening on these diagonals, on those slants?
It's getting hotter.
Okay, it's not only getting hotter, but what is temperature the measure of?
Average kinetic energy.
All right, so average kinetic energy. So what's happening here? Increase in kinetic energy, increase in kinetic energy, increase in kinetic energy. And so as you go from solid to liquid to gas, the kinetic as you increase the heat of a solid, the kinetic energy is increasing. But when you phase change from solid to liquid, what do you see is not changing?
Kinetic energy.
So the temperature is not changing, therefore the kinetic energy is not changing. But what's happening to the molecules? How? Particles, well, they've already sped up. They've already sped up here.
They're getting farther apart from each other.
Okay, so what's actually changing? They're moving from here to here. I'm not breaking bonds. I'm not breaking bonds at all. Totally not. Huh?
The IMFs are getting weaker.
Okay, so the IMFs are being overcome. So they have a strong attraction for each other in this position, but in this position they have less of attraction for each other, so they're releasing some pent-up energy, possibly, or taking it in, but it depends on which way we're going. What is the energy of position? Just talked about it. Potential energy. So here there's a change in PE, change in potential energy, change in potential energy. Because we have to associate some sort of energy change as we go from solid to liquid, but sometimes energy change does not mean temperature change. Okay, so when we say energy change, sometimes it's just the relative positions of the particles. So these are closer together, these are farther apart, these are really far apart. Okay, so the position of them can actually cause an energy change as well. Cool? That's just an extra concept to start thinking about. And the reason that you cannot say the reason you cannot say kinetic energy is changing here is because kinetic energy is directly related to temperature. And so if temperature is not changing, you got to come up with something else, right? And the only really other form that we're going to be talking about is potential. And then and as we go up here. So as you go from solid to liquid to gas, what's happening to kinetic energy as you go? Not in terms of phase changes, but like relative amounts of kinetic energy for each of these. Okay, so this is low kinetic energy and this is high kinetic energy. Okay, so as a whole process though, would this be an endothermic change or an exothermic change as you went from solid to gas? Why endo? So I'm going to say energy is coming to the system, not heat specifically. It could be heat, it could not. But energy is going into the system to bring these particles from a low kinetic energy state to a high kinetic energy state. So anytime people are like, oh, I'm going to gas, it's exothermic. I don't know why there's this association of gases. When you're making gases, things are making heat and it's exothermic. If you think about the speed of the particles, you can see really easily it's from low to high. So then how do you get it to high energy? You put energy in, and that means it's an endothermic process. This is like the second slide or first slide on your notes. This right here. Find it? Yeah? Okay, so then going from gas to liquid to solid would be an exothermic process because you have to somehow release energy from the high energy kinetic energy state to the low energy or low kinetic energy state. Okay, so let's talk a bit more about thermo, and then I'll give you guys a break in a second because Tuesday morning, a long break, and mole day weekend, I know, party hard, mole day weekend. All right, so here we have the basic of what is the system, what is the surrounding. I'm not going to do extreme detail here. The stuff we're studying is called the system. The stuff we're not studying is called the system. I mean the surrounding. It surrounds the system. But these are encompasses the entire universe. Okay, so the first law of thermodynamics said, whenever you're ready.
The energy in the universe is constant.
Okay, so the energy in the universe is constant. So even though I can say, oh, I'm conserving energy, yeah, because energy in the universe is constant. It's neither created nor destroyed because it's constant. But I can still exchange energy between two particles or two substances within that same universe, the universe we live in. So if energy is going from the system to the surroundings, what kind of process is that? Endo or exo? Exo. And that's because the system that we are studying is losing energy to something else. This might be, give me an example of a system versus a surrounding. You have to do this a couple times in your reading guide, so look there or just come up with something. Give me an example, like a real life example. Hold on, ice pack. Give me one that's exo. Going with this example here, that's exothermic.
Hand warmer.
Okay, hand warmer. So what are the pieces? What are the systems and what is the surroundings?
The system and the surroundings is, I guess, your hand.
Okay, so your hand is the surrounding. You feel the heat. Like I was holding my coffee, hoping you guys would pick up on that. Okay, thank you. Coffee is hot. That is the system. The surroundings is the coffee cup in my hand, which would be the surroundings. Same thing for ice pack or cool pack. Or a hot pack. So if energy is going from the surroundings to the system, that would be endothermic. And what would the temperature feel like on the outside? Colder. A lack of energy here, because it traveled inside the system, means it leaves it colder. And that's sometimes hard for people to figure out, like, what does it feel like at the end? It just feels colder. Okay, so we already went through all of these. Specifically, I want to talk about, well, I'll talk about work in just a second. But when we talk about work in terms of chemistry, it's going to be based on energy to do something. So if you're pushing a wall and you can move the wall, that distance that you travel is work. Okay, it's basically because of work. There's something called, who's been in physics? Work is equal to force times distance? Nay? Okay, it's a true statement. Well, I'm making it up. Work is equal to force times distance. But we have forces in chemistry, but they're on the molecular level. What might cause pressure on the surroundings? What state of matter? Gases, right? And if the gases have enough pressure, they can actually force something to change in volume or force something to change its distance from where it relatively was before, like blowing up a balloon. That would be actually work done. So we're going to relate that. We've talked about these three already, and then we know that heat is measured in joules. And last unit we talked about what that joule meant. A joule is a Newton meter. A Newton meter is a unit of force, distance. So what do you see that directly relates to? Work. Okay, so we can relate work and joules because work can be measured in joules and it will be measured in joules. But in chemistry, we tend to change it to something called atmosphere liters. So pressure and volume. Okay, so we know the definitions. I'm not going over the definitions again. You guys can put a star on that if you want to look at. But internal energy is something that we did mention. And what was the symbol for that? Charles group. What was the symbol for internal energy? Delta E. And delta E is incredibly hard to measure because it's probably easier to measure the kinetic energy because we can kind of measure the temperature and say, oh yeah, that's the average kinetic energy. But it's really difficult to measure the potential energy, which is stored energy. You have to do a reaction to make it release all the pent-up energy or to change its pent-up energy. So a lot of times we can't measure that directly, so we measure a change in that. And that's why we always generally will refer to delta E, because like I said, delta meant what again? Change, so E final minus E initial. We're really concerned about the state function of delta E, so we can see a change over time. Thumbs up, you're good here. Okay, I'm gonna pick up my notes. Looking at this energy, this is called a potential energy diagram. Looking at it from reactants to products, endo or exo?
Endo.
Endo, because no.
No, exo.
Exo. I'm sorry, I like to agree with people without looking. You can see it's exothermic because what happened? Oh, how can you tell it's exothermic?
Because energy was released.
So how do you know that?
Because the products have more energy. Not the products, the reactants have more energy than products.
So if the reactants have higher energy than the products. That means the energy went someplace during the course of the reaction. Where did it go?
The surroundings.
To the surroundings. And if energy goes to the surroundings, that means Q, or let's say, Q for the system would be positive or negative if it loses energy to the surroundings.
Negative.
Negative. Okay? Delta H is another way to phrase that. We're going to kind of relate delta H and Q, because delta H is enthalpy, but, bless you, delta H is enthalpy, but it's actually a measure of heat. Well, Q is heat, so we can relate them directly. So delta H would be negative because this is an exothermic reaction. So this one's easy to see, reactants yielding the products. This one's a little different, but if you see the arrows going down on the enthalpy diagram that looks like this, arrows going down, and then you actually further see that it's got negative delta H's here, you can assume also that it's exothermic. It's just a different way of writing it. You'll see those occasionally. And we'll work with them some more. But if I asked for you to tell me the enthalpy difference here, how would you figure that out? You see the big enthalpy change of negative 286. What is that? So what is that? 242, or yeah, 242 kilojoules. Okay. Next one, definitely opposite, so endothermic. And what you're actually probably seeing now is there is a relationship between the reactants and products, and I think Lewis said the equation earlier. What was it? That relates the enthalpy of reactants and enthalpy of products. Okay, so delta H of reaction. So this is a reaction, reactants yielding to products. If the products are higher in energy, I'm just going to put high right here. Subtracting something lower energy, low, does that give you a positive or negative number?
Positive.
Positive. So positive delta H indicates an endo or exothermic reaction. Endo. So that's how that law works. This is called Hess's law. And Hess's law has 3 variations of it. That's Hess's law, like 2.0, I guess. We'll go over another Hess's law version later. But this is an equation you will have on your reference sheet. They expect that you know how to use it. But we'll talk about that in more depth. It's just whenever you see potential energy increasing throughout a reaction, it's got to be taking in energy. So what would the surroundings feel like in this case?
Cold.
Colder. Okay, good. Okay, so this is kind of what we just went over. You feel me? You got your definitions? Definitions I'm not going over. You guys can read again if you need to. I'm going to go through some math problems because that's what you're going to need from me today. So we know the signs for exothermic are negative. The sign for endothermic is positive. This can be Q or delta H. Either one will have the same sign because they are directly related. Okay, so work. Work in our case is about the force that a system exerts on its surroundings, or the force that a system exerts on this. The surroundings exerts on the system. So if you think about a piston, like think about an engine, and you got the pistons and they're being compressed. Combustion happens, and when the combustion happens, what happens to the volume of the gas? It expands, right? So if the gas is the system, and the engine piston block is the surroundings, and the gas is expanding, is it doing work on the surroundings, or is the surroundings doing work on the system?
It's doing work on the surroundings.
Okay, so if the system is expanding, like this is the system, and it's expanding, it's pushing, it's forcing the surroundings away, and whatever the container it's in is pushing it away. Well, that takes a lot of energy out of the system because the system is exerting all that energy on the surroundings. So we call that negative work because the system is losing that energy because it's pushing on the surroundings. Can you relate how that's negative? The system itself is losing energy because it's exerting energy to push on the surroundings. And this right here, this pushing, we call it delta V, because what do you think is happening to the volume when you push on your surroundings?
Changing the volume.
Yeah, you're expanding. You're changing your volume in an expansion. So it just means that the volume is expanding. Vice versa, if the piston compresses back down, the piston compressing on the system pushes on the system. Well, the system's not doing anything. it's actually getting energy back because the transfer of energy from surroundings to the system is occurring. So that's compression. Something like a piston again. And so the work in this case, the energy transfer would be positive because the system is getting it back. So this is a new concept, but we're going to work with this in chemical in equations now. Oh, and what is the unit that we just said for joules? I mean for work. Joules. Energy for joules. The work units are joules. All right, so this is how we're going to use work. Energy is equal to Q plus work. But what is work? Work. Go ahead and write this little or square that off as part of your new paper. Work in our case is the change of volume at a constant pressure. So at simply one pressure, usually it's going to be given in atmospheres. Volume generally will be given in, what do you think? Liters. And then when you look at that, what do you see is the unit for work right now? Okay, you see it looks like atmosphere liters. But we know atmosphere liters is not what work is supposed to be measured in. So there's a conversion on how do you get to joules. So 101.3 joules is equal to 1 atmosphere liter. Does that look familiar? Yes. It's all related to kPa. Right. So I'm not going to go through each individual step of the conversion, but if you know that you have atmosphere liters as your work unit and you want to get to joules, what do? Right. Multiply by 101.3 and that will get you to joules. And I'll go back up here to the rest of it and make sure you have that down first. So in this case, why do we need to talk about work? Well, work isn't going to be affecting the energy of the system. And the energy of the system can also be affected by the heat transfer in or out. So we have to consider both of them in terms of in the chemistry of it. So we can figure out if the entire system of the energy is increasing or if the entire energy of the system is increasing or decreasing. So we know that heat and work are not state functions, okay? They don't have deltas on them, right? Heat is just Q, work is just W. If it was a delta, then it would be changed. That would be a state function. So we can measure some heat and we can measure work. So that's why we actually can directly calculate delta E. Why did I tell you that we could not directly affect? I'm videoing right now, so you'll catch up. Grab papers from the back, specifically those back there, because those are the notes on that side right there. Okay, so we have to find a way to calculate delta E because it's not able to be calculated by itself. That's why we have to have Q and W in here. So we talked about how the compression and the expansion works. Let's go ahead and do. Can we do a question? I'll come right back to that slide I just skipped. So in this question, this is slide what? Slide. It's on the second page, you guys can find it. Okay. So, calculate the change in internal energy. So as you're reading, what does that mean? What symbol? Delta E. So question, what is the change in internal energy for a system undergoing an endothermic process? So endothermic means what sign? Positive, and what is this? What variable is this referring to? Q. So this is positive Q. So I'm just kind of labeling as I go. In which 15.6 kilojoules, so this is positive Q right here actually, of heat flows, and where 1.4 kilojoules of work is done on the system. So if work is being done on the system, is that positive work or negative work? Right, because from the perspective of the system, it is actually work's being done on it. So it's getting energy, it's getting work. So this would be positive W. So these two signs have to be established before you even plug it into the equation. It's simply addition and subtraction, right? That's it. But if you have the signs incorrect, you'll do it incorrectly. So Q is equal to E is equal to Q plus W. In this case, they're both in kilojoules. Slap them together, guys. It's really that simple. So what is that? 17.0. That's it. It's just you got to read to know if it's positive or negative. And I'll go back and do that slide I just skipped. Why am I recording to 1 decibel? Okay, because in this case, you count, and when you're adding and subtracting, you count decimals. And the weakest decimal or the lowest decimals win. There's one here. Okay, so before I move back, tell me, when a gas expands, work is negative or positive?
Negative.
Because it's doing work on the surroundings. When it's compressed, positive. Okay, so what did I miss back here? The law of the universe. Energy is conserved. So we're actually considering we're in the internal energy scheme again. We are always considering system versus surroundings. Whenever the system is gaining energy, the surroundings has to be losing energy. So you'll always see this plus minus. You have to indicate it. If it helps to always put the plus so that you remember to put the minus, do that. So when one is losing, the other one is gaining. And then in this equation we just talked about what those mean. Q can also be given in variable or in multiple variable form versus just in Q form. So if I gave you multiple variables, I might give you things like M, C, and delta T for you to get Q to plug into this formula, okay? What is M going to be, or what is C measured in here? What is it measured in? Units.
Joules per gram degrees.
Okay, joules per gram degree Celsius. T is measured in degrees Celsius, and M grams. You'll see that these relate back to the C value, right? So then, whenever you multiply MC delta T, what variable is left over? Joules, which is what Q should be measured in. But if Q is measured in joules and work is measured in atmosphere liters, you got to do a little wiggling to get back to joules so that you can actually add those up. So in thermochemistry, we have to use Celsius. And gases, you have to use Kelvin. So you got to kind of switch your brains back and forth when we do start to combine those. But other than that, we should be using Celsius for the next week or so. Okay? So get in Celsius mode for me. All right, so let's do one more of these. The system releases, okay, so what do we know right now? Okay, so negative Q. So a system releases that much heat while this much work is done on it. What do we know?
That's positive.
Okay, so it's exothermic, this much work is done on it, so it's positive W. Calculate the internal energy change, what would you do?
104 minus 125.
Okay, so 104 minus 125, because that's going to be a negative value. So, and I'm just going to write that here so that you guys have it, but I'm not going to show you the calculation. That's a J, by the way. Okay, and then tell me on the next one, this is the one I actually want to get to. Okay, so this one's going to encompass all your knowledge that you've gotten so far today. A balloon contains 313 grams of helium. So I'm just writing down my givens as I go. At a pressure of 1 atm, the volume of the balloon is, I'm going to say volume initial, VI. Work through this one with me, guys. 10 liters. The temperature decreased by that. So what is this actually?
Delta T.
Right, so this is delta T of 15 degrees C. As the volume decreases, so V final of 1840 liters. While the pressure remained constant. Calculate Q, W, delta E for the helium in the balloon. The molar heat capacity of helium gas is this. So I want to show you, this is equivalent to specific heat capacity. It's called molar heat capacity because in this case it's not per gram, it's per mole. But it's the same deal. You still use it the same way. Okay, so C, molar heat capacity is 20.8 joules per degree C. Alright, what do I do?
Q equals MCAT.
Okay, so overall, what are we calculating? What do you want to do first?
Q.
Q first, okay. So Q equals,
Okay.
okay,
Okay. So, is 113.
hold on. C is measured in what here?
Oh, moles. So you have to convert.
In this case, it's moles, right? Not grams? So what do you want to do first?
So you have to convert grams to moles.
Okay, so let's take 13 grams times 1 mole of helium is 4
4.
grams. Okay. Oh, yeah, I thought this calligraphy pen was going to work right. I'm going to go back to normal pen. Alright, so I'm not even going to calculate it. I'm just leaving it in parentheses. C, 20.8 joules per degree C times moles. Okay, so moles and moles will cancel. Grams and grams will cancel. Delta T.
It's negative 15.
Okay. So the temperature change went down by 15, so yeah, it is negative. So, what is it? Yeah, decreased by 15 degrees C. So then delta degree C cancels, so you're left in joules. But what is the value of Q? What sign is Q?
Negative.
Negative. And that value, you guys can calculate it, or I got you here. Yes. Q is negative 2,400. Nope, lied. 24,414 joules. Okay, so we have Q. You guys can double check my math there, but I'm pretty good at using the calculator most of the time. What's next? Okay, so W is, what is the formula for W? Roughly.
Change in volume times pressure.
Okay, there was something else there. Negative. Negative P delta V. Because whenever we cause a volume change, the work, and if that system is doing that work, the work according to the system is, it's leaving, so it's negative. So that's why you have to incorporate the negative in this case, in the perspective of the system. So, negative what? 1 atmosphere times
1910 minus 1840.
So V,
Oh wait. 1840 minus 19.
right, so you're doing V final minus V initial, so what is that, delta V? Negative 70 liters. Okay, so that's our V that's going in here, so negative 70 liters. So then we get negative times negative because this is a positive, so we actually have, is this a positive amount of work? Is it compressing the system? The volume, okay, so the volume decreases. You're going from big volume to small volume. So what's happening to the system? You're compressing it, so that makes sense that our work is positive. Yes? Yes. You can verify that. Okay. So work is positive 70 atmosphere liters. Okay. What do we have to do here?
Joules.
So how do I do that?
101.3.
So I told you the conversion was 101.3 joules is equal to 1 ATM liter. So I'm going to show you that as a conversion. 1 ATM liter is 101.3 joules. So that cancels, giving us joules of 7,992.75. And I'm keeping it out right now because I'm getting ready to add. I don't want any rounding error. So that's 7,092.75. But if I wanted to get these, like, I definitely should, for Q and W, go ahead and round because it's asking for it, but I don't want to round it yet because I'm going to add them. So in this case, delta E, Q plus W. Q is negative, so that's negative 24,414 plus a positive 7,992.75 joules, and so all I do is add that, or subtract that, so what should my sign be in the end? Positive or negative? Negative by a lot, actually. 17,300 joules, which is negative 17.3 kilojoules. On to 3 sig figs because of what? I probably should reach 2 sig figs. No, 15.0. Sorry, that's 15. Well, that is 15.0. Okay, he feels accomplished right now. Yeah? Stand up and take a break. I just talked to you forever. I'll start back in about 5. Go get some water. Talk to your friend. Maybe less than 5. Maybe like 3.5. 3.5 so we can practice. I'll probably get y'all's reading guides on Wednesday because you're probably going to use them today. So, what? The reading good? I thought it was really good. I only do like 5 a year.
It's really thorough.
It is very thorough. I mean, I just told you to go. I have candy and 2 pieces of gum. And a brown pen.
I love brown.
Brown pens. And a nice little crown. Oh, the jewels are the same.
Nothing good can come out of the jewels.
No jewels. Somebody stole the jewel. It was like
No.
Everybody have a good weekend? Yeah? Lots of sleep? That's something I did not do. I should try that.
You should.
Anything anybody wants to share? Let's keep it PG-13 though.
Unless you want to talk about politics.
Nope. Not on my, it's before 8 o'clock. Oh, it's 8 o'clock now, I guess. No. Not before 8 o'clock.
Wait till like Wednesday.
Ben Carson's crazy, am I right?
I haven't had time to keep up with politics yet. Not yet.
Just Snowfield the
He
bird.
thinks that evolution is the work of the devil.
No comment.
No.
Science conjecture.
Are they cool?
They're kind of against my religion,
Oh,
but they're cool still.
I'll have to look at them. Who designed them?
Banking.
Hmm.
B period or not.
Okay. You guys all ready to go on? We're going to be calculating, so pull up your calculators. Calculator. And I just have some little bit of background I want to give you, and then we will hopefully remember some of this lovely stuff. And I might go through an example first and then kind of backtrack some of the information. You guys have this conversion factor down. You're going to need this conversion factor. You know how many calories are in a joule? Or how many joules are in a calorie? Now you do. Just make sure you know it. And this number should seem somewhat significant. What is that number in terms of water? The specific heat capacity, C of water, is 4.184 joules per gram degree C. So the definition of a calorie, you ask the general public, they're like, I don't know. But the definition of a calorie is the amount of energy it takes to raise 1 gram of water by 1 degree C. What? So 1 calorie is 4.184 joules because that's the amount of energy it takes to raise 1 gram of water by 1 degree C. So on your banana labels, because we all know bananas have labels, how many calories in a banana?
7,000.
You guys don't know this?
100.
Like 100. Okay, let's just go equal. Let's say 100. So a banana is like 100 calories. How many joules is that? You say 418.
It's not.
But food calories are different. They lie to us.
Wow.
So this is it's right here. Sorry, I thought it was a secret, but it's not. It's right here.
No.
Whenever one big C calorie on a label, one big C calorie is actually 1,000 little calories. Little C calories. So when I say big C calorie, I mean capital C. Little C calorie, little c. So 1 calorie is equal to 1 kilocalorie, which is 1,000 little c calories, which is how many joules?
So 4 point, no. 4.
You can do it.
4,180.
Close one, joules, right? So in a banana, there's 100 of these big C calories. So how many joules are in a banana?
That number times 100.
That number times 100, which is Spell it out for me. 1, 2, 3.
Oh, there you go.
418,000 joules in a banana. If you put that on a label, nobody would eat anything. They would think they're eating like so many calories. So why do you think they do that? Because the general public does not know what a calorie is. So they're like, oh, I'll just put a big C calorie in there. They won't know what it is. But we do. So we're going to go correct everything we see. Like, this is actually 1,000 times greater. Yeah, that apple has, actually, no, a banana has, what, 100,000 little C calories in it. Banana has 100,000 calories in it. What? What? It's insane. So, okay. Yeah, we have to, like, eat water. That's it. That's it. Okay, we're getting ready to use this equation and this equation right now. And then we'll come back to this other junk. This other stuff. We'll come back to it. Let's go to the problemos right here. All right, calorimetry. And this should ring a bell. I kind of want to just pull some of this back to your forefront of your brain because you know this stuff. So, whenever you're given calorimetry problems, that means generally it's some exchange of heat between a substance and another substance. A lot of times, it's between a metal and water. Because the metal is dropped into this thing called a coffee cup calorimeter. It's a styrofoam cup. Okay? Why would we use styrofoam? To retain heat. It's a really, really good insulator. Sorry, so many people want to tell me that. Whenever you put some water in here, and then you put a piece of metal, the metal might be hot. So what is the metal going to do? It's going to give the water some love. Okay, it's losing heat to the water. The water is gaining heat. So if the system is the system is our metal in this case. The water is our surroundings. The system is losing energy, so that's exo. The water is gaining, so that's endo. And that's kind of established our little universe, our small universe. But how do you measure the heat exchange? You can't measure heat specifically. You can measure the other things. Okay, you can measure the temperature. This is the thermometer. So you can measure the temperature change. You can also mass it. This is supposed to be mass, okay? You mass it, and you know the C of water. So how actually do you get Q? You actually do Q equals MCAT. You can't count. You have to calculate Q. You can't measure Q. Okay, so whenever you're giving two different systems or two different identities, you have to do Q the system equals Q the surroundings. But in our case, we just established Q the metal is equal to Q the water. I think I put metal here. Yeah, I did. Okay. And we're going to decide right now who's actually negative, who's positive based off the reading. So if we know two Q's, that means we're probably going to be given two masses. We might know two C's. We probably will know two delta T's. We're going to set up MCAT equals MCAT. Metal and water. So I like to set up a nice little table on this. I don't like to just write out numbers. Some of us like to write out numbers, and that's totally fine. Do what you got to do. So MC delta T. Those of you in my honors chem class, this is how I did it in the past. Okay, so in the reading, what's the specific heat? Okay, so what's the question? We'll call this metal and this water. Which of these is the question? C of metal, okay. 500 grams of metal, 50 grams of metal. That raises 100 milliliters of water, so what is that in mass? 100 grams, because the density of water is 1 gram per milliliter. So this is 100.0 grams of water. And a calorimeter from 34 degrees C to 36 degrees C. So that's for water, right? What is delta T of water? 2. So 2.0, so 36 minus 34, so you're doing final minus initial. So that's 2 degrees C for water. The initial temperature of the metal was 95 degrees C. The final temperature of the water in the metal is 36. So what is the delta T for the metal? Is that 59? Okay. So 59 degrees C. Okay, so why is there this empty spot here?
Because you know the specific heat.
What do we, oh no, you don't look in the textbook, you know this.
It's 4.18.
4.184 joules per gram degree C. All right, let's crank this out. Let's do it. Use this information. What am I solving for? I'm going to rearrange this. Go ahead and rearrange this. C.
Metal.
Okay, equals Give me variables first, and then we'll plug. So MCAT for water over MAT for metal. Okay? Which of these is negative? Which of them is losing energy? Metal, because this should be negative, by the way. Sorry. 36 minus 95 is negative 59. Yep, so this is exothermic. So this should be negative Q over here. But the negatives always cancel each other out. It really doesn't matter, but I'm going to put the negative right there just to make sure we see that one's exo and this one's endo. Okay, so then plug. We have 100 grams, 100.0 grams, 4.184 joules per gram degree C. Delta T is 2 gram degree C over negative, what was the mass? 550 grams times negative 59. So you can see, point proven, the negatives do cancel each other out. And that would give us C of metal. Give me an estimate before you calculate. What can you simplify in your math? Okay, so the 200 over 50 gives us what? 4. Okay, so that's 4. Good Lord. Okay, so this is 100 times 2 is 200 over 50 is 4. 4 times 4.18, right? And about 16. Yeah? So that's on top, 16 on top. Over about 60. Small number, right? 0.2, 0.3. I'm not sure. Probably. 0.25. Yeah, so that's about 15 over 0.28. See how awesome you guys are? You can do math mentally. Yeah? You don't feel any more confident about this, do you?
No.
You've got to try to show yourself that you can do it. We just did this. It's Tuesday. It's like halfway through the week already. Okay, so this should be generally your C of metals. Metals have a really, really low specific heat capacity. So what does that mean about their rate of heating? Right, so metals heat, this is a low C, so they heat, not heat, they change temperature quickly. Okay, so if you go to the beach right now, let's go. Go to the beach right now. Temperature of the water, nice or not so nice?
Not so nice.
No, it's probably really nice still, guys. It's only been like, a couple weeks into fall. The temperature, the specific heat of water is 4.184 joules per gram degree C, right? So it's going to take a long time for it to lose that internal heat so that it would change its temperature. It's probably like a good 70 degrees, 60 degrees right now. Not bad. But if we go in February, it's been 3 months of winter, and that's been plenty of time for it to lose all of its internal energy, so the temperature would change. But if you set a piece of metal outside right now, it would get cold in 5 minutes. Metals have such low specific heat capacity, they change temperature very quickly. Okay, let's do another one. Let's do... Oh no, I gotta go back. Okay, so we did the one that I really wanted to do. Let's go back to the beginning, and then I'll see what we actually need to talk about here. Because you guys got a lot of that. Sorry, this is a lot of... am I going the wrong way?
Who knows?
Who knows? There we go, okay. So we have this information in front of us. What do I need to go over right now? This is the math part of it. Thumbs up when you're good. Thank you. I just need your assistance. This is all exactly what the Q to the surroundings versus Q to the system. One is positive, one is negative. And calorimetry, the practice of calorimetry is based off the first law of thermodynamics. TD is thermodynamics. So we're good there. This is new. This right here. That you've seen on your reading guide, but we've not used it. There's a significant difference between this capital C and this and this other lowercase c we've been seeing. This is heat capacity. Heat capacity is generally going to be applied in a calorimetry experiment and a bomb calorimetry in that case. So we're going to kind of mention like constant pressure calorimeters and constant volume calorimeters. What do you think we're going to use in class? Do you think we're going to use a bomb calorimeter that has a combustion experiment inside and its volume goes really big? Yeah?
Yes.
No, we don't have bomb calorimeters. We have these nice coffee cup calorimeters under this constant pressure that we live in called 1 atm. That's what we have. Okay? Bomb calorimeters, they have them at Duke Energy, and I saw them. I'd never seen a bomb calorimeter until I went there like 3 years ago. And I was like, what? I've never seen one, but now I've seen one. Yeah, they have them. No, it's a little desktop. It's like little mini. It's a steel drum, and they put some pure oxygen in there. They combust their coal to see the amount of energy that the coal can make. So it's for real. All right. So anyway, the constant volume is because it's a steel drum and that they're combusting these things in, so that cannot expand. So therefore, it's a constant volume. We're going to be using constant pressure ones, which is coffee cup calorimeters. But anyway, whenever we have questions, a lot of times they'll refer to bomb calorimeters, and those have constant volume. So whenever we have constant volume, that means zero work is being done because there is no delta V. You see how this relates to this? Yes? Okay, so if you have no delta V, you have no work. So the only thing that's related to internal energy change is the change in, or the amount of heat exchange, which is Q. So in this case, we can actually calculate Q just like normal. Q equals MCAT. But a lot of times we're not given the mass of the calorimeter because it's not, it's already got the mass embedded in the amount of heat that's put out. So this Q equals CAT is something that we're going to be seeing with bomb calorimeters. So whenever you do something like this, tell me what your units are. Big C.
Joules over degrees Celsius.
Thank you. Joules over degrees Celsius times,
Degrees Celsius.
right? Delta T is in degrees Celsius. So what do you get?
Joules.
Joules. Okay. This is probably going to be given to you in a word problem that also talks about what was combusted. So let's say propane was combusted. Let's say 40 grams of propane was combusted. So 40 grams of propane, which is what? C. 3H. Okay. So that amount of propane was combusted. I would say that, let's just call it a negative 1,000. Negative 1,000 joules. So exothermic reaction of 1,000 joules, aka 1 kilojoule. Negative. If that amount of heat was put out of the combustion reaction per 40 grams of propane, you actually can set up a ratio to say how much heat is released per mole. So this is not 40. Is this 44? Is this molar mass 44?
Yeah, it is.
Thank you. I meant to say 44, not 40. Okay. So if I told you this amount of heat was released per 44 grams of propane, that's actually per mole of propane. So we actually set up something called the heat of reaction, which is measured in kilojoules per mole because it accounts for the mass or the number of moles of the reactant that was combusted or whatever the reaction was in this case. So we actually could say, okay, I know how much heat was released, I know how much the stuff weighed, so that would be 1 kilojoule released per 1 mole. So therefore, the delta H is negative this. I set up a really easy math here, but you're basically just counting per mole of it. So the heat of reaction, that can come in many varieties. So what are some reactions that we've done before? All right, combustion. Great, guys. Delta H. Combustion. One more. Give me more.
Synthesis.
That would just be, so synthesis reaction and decomposition reaction would just be called delta H reaction. What about acid-base? What do you call those reactions that acids and bases react? Neutralization. That's called delta H neutral. Okay, so there's a couple that you will see like this. If you make a solution of something, you put powder into solvent, you make solution, it's called delta H of solution. So we have all these different indicators to tell us what kind of reaction it is, but a generic one is just RH simple reaction. And that's what this is. Okay? So this is kind of what I just told you. If I give you in a situation where you can find Q, first step is to find Q. This is your friend. You will probably forget how to calculate delta H. Enthalpy is what this is. Find Q, find the moles, divide. That's all you have to do. And that's going to be something you will do a lot. And that's usually only whenever it's considering, if it's asking for molar heat, if it's asking for H of reaction, If it's asking for anything per mole, you have to figure out the moles and then divide. So that's just called molar heat capacity when we have to use the moles. But other than that, we have molar heat of reactions, and that's what we just talked about. So I have a question based on this in just a second. So finish looking at what you need to here. These we kind of already did. Remember this from the heat curve we just drew?
Yeah.
We talked about phase changes. We talked about the energy of that phase change. And that's based off not kinetic energy changing, but on potential energy changing. So potential energy. Two or three that you should be aware of, specifically for water, are these. So circle them on your paper. Whenever we deal with water, generally we're asked to just know those, and I will give them to you if you don't, but on your homework, you're going to have to look it up or look at your paper here. So delta H buzz, so fusion of water, so state of matter, solid to liquid, is 6.02 kilojoules per mole, and then for liquid to gas, for vaporization, is 40 kilojoules per mole. Why in the world is it like 4 times greater here, or like 6 times greater?
Because it takes a lot more energy to convert to gas.
Because, yes, huge amount of intermolecular forces that are totally being overcome. Going from solid to liquid, you're moving like this much, right? Well, there's still intermolecular forces holding that liquid together. How do you think it's still a liquid? They're attracted, right? So there's still inner IMFs. You've only kind of overcome them maybe about 10% of it. But when you go from liquid to gas, you are totally wiping out all IMFs. The gas particles are so far apart. It takes a lot. There's a lot more change in the potential energy. Okay, so other values you should know. These are the delta H's for water for phase change. Only for phase change. The other ones were, sorry, I'm going back and forth a lot today. This right here for specific heat capacity of water, and that's one that you'll use probably more often than not. The states of matter, though, for water have different C values. So the one we generally refer to is liquid water, which is 4.18 joules per gram degree C. The one for gaseous water and solid water, ice, have different values. So if you ever have to deal with something that is at a specific state, you have to use the specific heat capacity for it. So the specific C. We will go over this. We'll go over that later. We already know how to calculate delta H at this point. So let's do one more for kicks and giggles, and I think we'll be good. This is just some information on calorimetry if you guys want to read. Okay. Example. Last towards the end. So 28 grams of a substance with a molecular weight of that is placed in a bomb calorimeter. Woo, we're going to combust something, right? With the heat capacity of this. So let's write down our givens. I'm ready when you are.
Mass equals 28 grams.
I'm going to try this again. Mass is equal to
28.
Okay, so I'll just write molecular weight just for us for later. What is the variable for heat capacity? What kind of C? Big C. Make it exaggerated so I understand what your chicken scratch is, people. 2.60 joules per gram degree C. Oops, I don't know what that is. It's there though. Okay, it's combusted, all right? What is the molar heat of combustion? What is that asking for? This is where vocabulary comes into play. Molar heat of combustion. Okay, say again?
Kilojoules.
So I'm looking for kilojoules per mole, right? Molar heat of combustion. But what variable is that? Delta H, specifically combustion in this case, just because I say combustion, but it is delta H reactions for general purposes. So we're actually asking for this, guys. You have to be able to know what that vocabulary stands for. Okay, for the substance, if the temperature of the calorimeter went from 25 degrees C to 142, what do we know from that?
Delta T equals 117.
I believe you. 117? Okay. Convert joules to calories. Okay. What's first step, guys? Knowing we want to get to delta H. What did I tell you your 3 steps were to get to delta H?
Find joules.
Find joules.
Find moles.
Find moles.
Divide.
Cool. Find joules. How do I find joules?
Max. Because no, it's not math. C math.
Cats?
Cat.
Cats.
Cat.
Okay, this is when chemistry cat comes into play, guys. Q equals cat. I'm ready when you are. Q. Thank you. Whew. We're really working on that reading. I know. You guys are good there. Next. 117. And this is this is increasing in temperature. So this is it. This is, it's increasing in temperature. The calorimeter is increasing in temperature. I'm going to note this as cal. Okay, this is the calorimeter. Note this as cal because you're going to eventually be seeing this and doing this on your own. I want to just tell you what this means afterwards. So somebody calculate for that for me. I have mine someplace over here. Three or 4 joules. So the Q cal is equal to 304.2 joules. So that's the amount of heat that the calorimeter absorbed. You see, it's a positive value there. Who gave it to the calorimeter? The combustion reaction, right? So this means Q of the combustion. It's the same magnitude but different sign. Right, so negative 304.2 joules. And this is where people mess up. They forget to put the negative. And it's because we have to always keep in the back of our mind system versus surroundings. You should always be saying, okay, here's the surroundings, the calorimeter. The system is the chemical of interest, in this case, combustion reaction. So this is Q. All right, so we got Q. Next.
Moles.
Okay, so we're using this information, 28 grams times 1 mole, and that is, I think, 4, nope, what is that? I didn't actually calculate it, I did it all in one step. Somebody do that for me.
0.538.
Of this substance that was combusted. Okay, so got Q, got moles. Divide, so negative 304.2 joules divided by 0.5385. What is that? It doesn't have to, but we can convert it in just a second. I'm keeping it in joules for now. This one, this variable, or this unit here can't be joules. What is that?
564.9.
So negative 565 going to 3 sig figs. Yeah, joules per mole. Okay, so that's how much energy is released when 1 mole of that substance is combustible. That's a lot of energy. That's like so that's negative 0.565 kilojoules per mole. The question also said convert to calories, and that was let's go to little c calories first. So give me little c calories. So what do I do? I know you guys know what it is. So I'm converting, right?
So times 4.18.
So times 1 calorie over 4.18 joules, and that will get you to calories. So I'm just showing you the conversion process there. Now get me to big C calories. I'm to little c calories right now. So 1 big C calorie is worth 1,000 little c calories. Okay, and this is going to be how much energy they put on the nutrition label. So this is they would not put this on the nutrition label. This is really small. They would do this per serving, which is probably a lot more than 1 mole of whatever that substance is. But that's how they determine the nutrition value of food. They put it in a bomb calorimeter, they explode it, they figure out how much temperature change, they figure out how much heat was released, they relate it back to calories, they pop it on a nutrition label. That's what food chemistry is. Woo! You want to do that for a living? There's also flavor chemists. They make things taste like things that aren't those things. They lie. They basically lie all day. It's not what it is. Yes. Okay, I'm going to stop for now. You guys, we have like less than 10 minutes left in class. So what I'm going to go ahead and show you is what you're responsible for me for tomorrow. So start working on the work energy columns that find it. I labeled them for you, 1 through 10. Yeah? You see that?
Oh.
Look for it. And put a star next to the work energy. Kevin, this back there. You need to grab the other side. Okay, so work energy is that first problem set. You see it? Yes. You see the answer key down there?
No.
Yes. All right, so you should be able to check yourself so you don't wreck yourself. Second is the heat problem set. I think it's 5 questions. Is it 5? 6? Oh, 6 questions. Yes, so it's the first. Oh my. Okay, look up here if you're confused. You are doing the first, and if you staple these in order, you will have no problem. First problem set, answer key below. Second problem set over here, there are 6, it says heat transfer problem set / lecture notes. I think we did one of them. Did we do one of those? Yeah, we did number 1. Yay, we've already done number 1, so it is a 5 problem. It is a 5 problem set. And the answers are not on that one. Sorry. You guys can do that. I'll see if I can post the answers tonight somehow. So that's what I want you to start. So basically, if you can get all those done, you're in good shape. After that, tomorrow. Okay, so you guys are going to finish working on that. So if you need to save a question or 2 to work with a buddy on, that should be fine. You're going to take notes on these 3 videos. They're about 10 minutes each. Okay, the Bozeman Science is really good. He's kind of goofy. This guy I've never seen before, but it was a good video. It was short and concise for what I need you to learn a bit by yourself. And then the last one. These are basically 3 different concepts, and I'm going to recap them all on Thursday. Okay, so just try your best on that. Take notes, write down the examples in the notes, and then after that, you can start on the Hess's Law problem set, which is right below. Do you see the Hess's Law problem set? It's not only one question. Look further. Do you see the rest of them? Okay. Hess's Law is really easy. It's a summation of BCEs. So on a BCE, like in our redox BCEs, if something was the same on the left and the right, you could cancel them. Yeah, like 2 waters on one side, 4 waters on the other, you cancel 2 of them. It's basically the same thing, but it's for thermochemistry instead of redox. It's the same story. So that's what I want you to do tomorrow. Does that make sense? Yeah. Okay. The other thing, and I would like for this to be done by I think by Friday. There's this NSMI National Science Math Institute. Hold on. And it looks like this. National Math and Science Initiative. There's some great reading here. That's all great and all. But I want you to be still getting more comfortable with this thermochem stuff that's kind of new. So if you can attempt some of these exercises, I'll ask for you to do the ones that you feel you need to. Be a reflective learner, check yourself on the answer, and go for it. There's a couple that we have not gotten to, like only 1 through 7 we've gotten through today. Yeah, 1 through 7, 1 through 6 mainly we got through today, but I will ask you guys to do a couple of those throughout the week. Okay, so you guys can do this without me tomorrow? Don't cry, no. It's going to be a rough day. Other than that, we're done.